Hey there, welcome back. So let's continue with the flat play, the transitional flat play case. So I will launch Fluent. Remember now we're working outside the bubble of ANSYS Workbench. So we want to, I will run in ANSYS Fluent standalone. So this is a 2D case. Okay, I put here my directory where I have everything. Choose the number of processors here. I will put 4. Okay, I have 4, so I will put that one. So let's launch. So just a reminder that if you download the cases, you're going to find here the Fluent case ready to go. So this is what we are going to use. Plus we have there the additional validation data and some outputs I put there to compare now. So we have different solutions, different models there that later we're going to see. Okay, so in my case, Fluent is ready. Okay, so I will open the case. Okay, and the case and data probably, yes, so why not? So when you see the data there, usually means that you have the solution. Okay, so now I load the case, and first let's take a look at the mesh. Okay, so put there, select everything, and this is the mesh, and look at that. It's a very, very fine mesh, now in the direction normal to the wall. Not so fine in this stream wise, okay? But let's say that is fine enough. You can do something finer for this. Well, for this case, it is okay. But remember that in transition, it's also important that direction, and this you have also the third dimension. It's also important to resolve there. These white lines represent now the sampling points. So already create those lines there. So at this point, let's take a look at the case setup. Okay, so we have our traditional. I like to work in this vertical workflow here. So here nothing changed. Okay, so I'm not going into detail. So then you can check the materials here if we would recall. But the important here is that check the turbulence model. So we're going to work in transitional models and see here that you have different options. Okay, so you have the transition KKL omega. It's a 3 equation models. We're going to run with this one, the transition SST, which is a very good one. Okay, but it's up to you not to judge which one is the best one. And here we have also a few corrections that later we're going to talk about in more details about those corrections. And just to mention that you have a source model here. So you go here, K omega SST. See that you have the option to enable, and you have the gamma transport equation, something that as well we address a little bit in the theory. Okay, so this model is lighter than the transition SST, but also have a few advantages because they include here this cross-flow transition. Okay, so you have cross-flow. Okay, so it's up to you to play with these 3. I will set up this one. This is the one we're going to use. And at this point, that is the only thing that I wanted to show you. Now we go. The other thing that I need to mention is here you got boundary conditions. Again, remember that you have a turbulence model. You need to give boundary initial conditions. So here there is a new initial condition and boundary condition, which is for the intermittency. Okay, so it's that variable that is going to define where do you have laminar flow or turbulent flow. Okay, so here you have it. It is bounded between 0 and 1, and it is recommended that to initialize and at the inlet to put it 1. Okay, it might seem a little bit counterintuitive, but this is a standard practice. Okay, so put it to 1. Then also just to mention that transition to turbulence is very sensitive to the turbulence intensity level and this quantity. So you also advise you to play with the values, and you will see the influence. But here we're using the values from the experiment. Okay, from the experimental data. Okay, so that's all. Then standard numerics. Here we're setting everything second order. As we are solving this new model, we're introducing 2 additional equations, one from the intermittency and the momentum sickness. So here we set up how to solve those. Nothing to do here as well. We should pick up the default values. And as usual, remember to set up your monitors. So here we're setting a few monitors. Okay, so here we're sampling in a line. Watch your stress, density, mu. Okay, so that is just a standard sampling. So at this point, we can initialize. We can take the default value. So remember that we initialize everything with 1 in intermittency. And that's all, okay? So at this point, we'll give you a warning there is one. You can just try to set up that one. But for this case, it does not matter. So let's run, okay? So at this point, we're using the default. Again, also, you can try different numerics. Okay, my goal is not to show you a numeric, but different methods that will give you different convergence rates. You should arrive to the same solution or similar solution. So at this point, let me press calculate, and off we go. So see that we have all the monitors, okay? So see that, as I mentioned, that you have new equations, okay? The rate theta intermittency, I'm not going into details, we address that in the theory. Something, a small warning here, that intermittency is difficult to make converge, okay? So don't be afraid that that is not, the residuals are not going down as the other quantities. This is difficult to converge, and usually you will get these behaviors, okay? So it's not a big problem, but remember always, but look at that, all the other quantities are converging very well. But it's always what you need to check is just integral quantities, okay? So see that we have it's already converged, okay? Well, it didn't converge, arrive to the maximum number of iterations, but see that Y plus is not oscillating. Y plus, remember, is a direct indication of wall shear stress, okay? It's related to that. CD as well, we need to change the scale, but it should be very steady, the behavior. So we can take this for granted as a good solution or a steady solution. And now we can do the traditional post-processing now. So see that turbulent viscosity ratio, what I mentioned, that this quantity is important to look at the mesh, okay? So just to show you that, and let me draw the mesh. Okay. How about that? Okay. So the colors, that doesn't help, but as it mentions that this turbulent viscosity ratio, remember that turbulence peaks somewhere in the buffer layer, okay, is very energetic. So to look at your mesh resolution close to the wall is good enough. You look at this. So see that in this case, this mesh is very, very fine. So its strength is more than good, okay? But in one case is you realize that, see that is peaking somewhere here, okay? Probably the midpoint of your turbulence, the boundary layer will be somewhere here. So as you see that is you have just one or two cells in this region, that means that is not a good mesh, okay? So you should refine it. So in this case, this is a quite good mesh, and you can take a look at also on this field. Okay, let me put here auto range, probably. Okay, probably we can see better here. So see that somewhere here is peaks, the turbulent viscosity ratio probably would be also the midpoint of the boundary layer. But see that is a very good mesh, okay? So this mesh that is resolving, even as you go here, see that you're clustering enough cells to resolve now the velocity gradient normal to the wall. And the other quantity to look is here, you have your traditional quantities. So the other one to look here for, it is this one, intermittency. Okay, so this one is the one that is telling you where let me now switch off the mesh. Where do you have laminar or turbulent flow? Okay, so see that here, all this region, okay, it is laminar. Okay, so see that it's a sizable region normal to the wall. Then usually you see this behavior means already the transition here, and see that it now is transitioning to fully turbulent. So see that the laminar region is becoming thinner, okay, and so on. So this is the idea of these models, okay? So you add those quantities that has been calibrated using some experimental correlations, and then it will find where do you have laminar or turbulent behavior, and according to that will set a given correction in your turbulence model. Okay, so now just to do as well the traditional validation. So recall that if we mentioned that we can do these plots to regions. So we have all the sampling there already enabled. I'm not going into details. We have addressed that a lot. So I can go to plots and I should have those there already. So let's see that. Okay, so first I have the skin friction, the flat plate. Okay, so see that we have that evolution there, but also remember that you should have there the validation data so you can open that one. So here we have Reynolds, okay, in X using the length, flat plate length. Also you have it in function the actual distance, not in the Reynolds. So let's read the data. Okay. And voila, this is it. Okay, so see that we have a very good agreement, and then we are going to have the other plots. So in this one, okay, so see that this will be line 8, if I will recall, should be the turbulent region. Okay, so in any case, let's plot this data. So Okay, so let's plot this profile, okay, this Spalding profile. Okay, so see that comparing with the Spalding profile, see that we have quite good agreement there, okay? So see that in this case we have, it's not say that the Spalding profile is the good one, okay? But see that between these two, we have a large deviation difference in the buffer region, okay? That's why we avoid it, because that buffer region, precisely, there is not a universal or a good enough fit in there. So all the models will have the largest differences here. And this small deviation can account for a lot, for 10, 20% of error that you are going to carry into your turbulent region. Okay, so, and now in plot 3, okay, so this, okay, the flat play, okay, coordinate. So I would like to see what all the plots. Okay, so line 9, this should be the, okay, the other laminar. Okay, so I will use this one. Okay, and so see that this is the laminar profile. Okay, so let me load also the laminar. So let me load everything here. And see that in this sampling location that will be, you know, the location where the flow still is laminar. See that this is what we have, okay, following the laminar law, okay, as expected. So this is it now, our validation. And just to show you here the comparison with different solutions, okay, so here I already have put here in Fluent case outputs, okay, so we have a different cases. So see that here I will open this, and this, okay, different models. And let me open also the validation data. And voila. So look at what we have, okay? So we have the transition model, SST, okay? And then also the other model, the SST intermittency, okay? The 3 equations. And see that these both models here are giving a relative good results, okay? With some differences, but it's something acceptable. But now if we look at the laminar solution, okay, this will be like pink, I think. So see that the pink line is following completely this laminar behavior, okay? It's not doing the blending. And something similar will happen with the, here, see that it's happening with the SST, the fully turbulent. So the SST fully turbulent, okay, is not doing the blending to laminar, is staying in the turbulent region, okay? So it managed to predict relative well the turbulent behavior, but doesn't manage to predict this one. Same happens with the laminar. It managed to predict very well the laminar behavior, but does not predict very well the turbulent behavior, okay? So the only models that manage to predict this transition to turbulence are those models specifically calibrated for that. You might be able to use eddy viscosity models now, but nonlinear eddy viscosity models to solve this. Also using some very specific less models, okay, like very well calibrated for wall-banded flows. But if you go to less, you will need to switch to 3D, so it will be very, very expensive because 3D also unsteady. Okay, so this is this case, okay, very interesting case. I invite you to play with different models, okay, so you have the options. So here I didn't show this model, the K omega, here the gamma, yes, this is the intermittency should be this one. I didn't use this one, okay, you can run that, okay, and then you can compare also with different turbulence models, parallel armadas, KX, and you will see that you won't get this switching, okay. Then you can also do the traditional post-processing, okay? And this is it, okay? This is transition to turbulence. You also have here the mesh, so you can, from this mesh, you can extract the geometry and redo the mesh, something finer or quarsor, and you will see the influence. Now, if you use a quartz mesh, you will see again that you are not going to be able to capture that transition. And finally, remember that there is an external influence with inlet conditions. So if you change these values, in particular no turbulence intensity, you will get different behaviors here. So large turbulence intensity are going to onset immediately the turbulent flow. Okay, so you're going to see that this curve will be here like the SST. And if you use a very low value, okay, likely you are not going to onset the transition to turbulence. Okay, talking about using the transitional models. Okay, that's all for your case, for this case. Thank you very much. See you next time. Bye.